NASA unveiled pictures from a new space telescope capturing the deepest images of the universe anyone has ever seen.
Deep in the abyss of space, a revelation unfolded, one so profound it rattled even the most seasoned astrophysicists. The James Webb Space Telescope, humanity's most advanced eye on the cosmos, pierced the veil of deep space and stumbled upon a discovery that defied the very bedrock of astrophysical understanding. This was not a mere curiosity or intriguing oddity. It was something that, by all known laws of physics and cosmology, simply should not exist. Webb's instruments captured the light from an object so profoundly incompatible with existing models of the universe that it forced scientists to re-examine the fundamental nature of space, time, and matter. The event began when the telescope peered into a distant region of the cosmos, an area teeming with the faint glow of the early universe, light that had traveled for billions of years, emitted not long after the Big Bang itself. Webb's powerful infrared sensors were designed to see the universe's infancy, revealing the oldest and most distant galaxies like a time machine gazing at the cosmos awakening from its primordial slumber. Astronomers expected to observe the first, chaotic, small galaxies just beginning to form. Instead, nestled in the shadows of deep time, they uncovered an enormous, fully mature galaxy. It appeared impossibly ancient and well-structured, with spiral arms and a defined core, features that should only form billions of years into cosmic evolution. And yet, this galaxy existed when the universe was less than 400 million years old. This discovery wasn't just an image of history, it was a paradox. The early universe was thought to be a chaotic soup of particles, radiation, and nascent structures. Stars were expected to be massive, short-lived, and scattered across irregular, primitive galaxies. But this new finding pointed to an accelerated evolutionary process, or perhaps an entirely different mechanism of galaxy formation. If such complex structures formed so early, it meant that dust, heavy elements, and stable star systems were present much sooner than previously believed. Stellar nucleosynthesis, the process of creating heavier elements inside stars, must have occurred at a pace that defies current models. Either the first stars lived and died faster than we imagined, or an unknown force sped up the enrichment of the cosmos. The implications were staggering. Could dark matter have played a more dynamic role in shaping these early galaxies? Was there a fundamental flaw in how we interpret redshift, leading to incorrect measurements of cosmic age and distance? Or were we witnessing signs of new physics, perhaps modifications to gravity on large scales, or the existence of parallel universes bleeding into our own? The mystery deepened when follow-up observations showed this was not an isolated case. Webb began to detect more of these early galaxies, too large, too luminous, and too structured to be explained by standard theories. One particularly baffling feature was the light signature. Instead of pure hydrogen and helium, the expected ingredients of the first stars, the spectrum revealed carbon, oxygen, and even traces of iron, elements forged in stellar cores and spread through supernovae. For them to exist in such abundance, entire generations of stars would have had to live and die, far too quickly to align with accepted models. Even more astonishing was the galaxy's structure. Its elegant spiral arms weren't the chaotic swirls of early cosmic debris but graceful features orbiting a bright, stable core. This level of organization required hundreds of millions of years of gravitational interaction and stability, conditions believed impossible so soon after the Big Bang. The notion that supermassive black holes, which anchor galaxy cores, could have formed and matured this quickly further deepened the mystery. The galaxy's behavior added another twist. Its light curve, changes in brightness over time, suggested it hosted an active galactic nucleus or even a quasar powered by a supermassive black hole. If such energetic processes were underway so early, the conditions for black hole formation and growth must have differed drastically from current theories. This forced a reassessment of the timeline for the birth of these cosmic giants and the environments that nurtured them. Furthermore, the galaxy's rich chemical composition hinted at the possibility of early planet formation, and by extension, early life. If galaxies formed this fast and contained such diverse elements, the building blocks for rocky planets, water, and carbon-based compounds may have existed billions of years earlier than previously believed. That stretches the timeline for potential life across the universe far beyond what scientists had imagined. Thanks to the Webb telescope's unprecedented resolution, astronomers could map individual star-forming regions and trace gas flows within the galactic arms. What they saw wasn't just a mysterious galaxy, it was a radically different version of the early universe, more mature, more active, and more structured than the standard cosmological narrative allowed. It was as if Webb had tuned into an alternate timeline of the cosmos, revealing a universe that evolved by an entirely different script. And what made this revelation even more shocking was its statistical improbability. If this galaxy were a one-off, it might have been dismissed as an anomaly. But more galaxies like it kept appearing. Each new detection strengthened the possibility that this wasn't an exception, but rather evidence of a hidden chapter in the universe's history, one that had remained unread until now. This was no mere update to existing theories. It was a seismic shift in our understanding of the cosmos. The James Webb Space Telescope didn't just find a galaxy, it uncovered a profound inconsistency in our grasp of time, matter, and the fabric of reality. It presented a galaxy that, by all calculations, should have taken twice the age of the universe to form. And yet it had done so in a fraction of that time, shining across billions of light-years to tell us that our cosmic story might need a dramatic rewrite. As models scrambled to catch up with observations, some scientists began exploring more radical possibilities. Could this be evidence of a previous universe reborn in a cosmic cycle? Was it a remnant of a pre-Big Bang epoch preserved through unknown laws of physics? Or was it something even more astonishing, a glimpse into the infinite complexity of the multiverse, where the rules of reality themselves can vary from one universe to another? One thing became clear: the cosmos still holds secrets we are only beginning to uncover. Deep in the fabric of space-time, scientists are now grappling with the potential effects of higher-dimensional phenomena, concepts once relegated to the realm of science fiction. These theories suggest that structures from other realms might be imprinting themselves onto our own universe. Once considered fringe ideas, such hypotheses have become necessary lines of inquiry in light of observational evidence that simply refuses to be explained by conventional astrophysics. This impossible discovery recorded by the James Webb Space Telescope, JWST, is far more than a mere anomaly. It's a direct challenge to our most deeply held assumptions about the cosmos. It questions the notion of a singular, predictable timeline and introduces the unsettling possibility that time itself may flow differently in various corners of the universe, where galaxies might be forged by laws we have yet to uncover. With this discovery, JWST has done more than illuminate deep space. It has exposed the vastness of our ignorance. As each new wave of light from the anomalous galaxy reaches JWST's sensors, astronomers are left with more questions than answers. The data have become a catalyst for a thorough re-examination of astrophysical models. Researchers across the globe are now recalibrating simulations, cross-referencing existing records, and searching for a framework that could explain such a galaxy's existence. But for now, this singular discovery remains an enigma carved into the very fabric of reality, a haunting reminder that even with our most advanced technology, we are only scratching the surface of the universe's mysteries. The photons that traveled billions of years to reach us did not offer a clearer picture of cosmic history. Instead, they acted as a mirror, reflecting how little we truly know. The moment JWST recorded this impossible encounter, a new era in astronomy began, one that diverged rapidly from the well-established narratives of cosmic formation. As additional data emerged, researchers came to understand that this discovery wasn't an isolated quirk, but the first fracture in a vast wall of unchallenged assumptions. This galaxy's internal consistency was particularly shocking. Its rotation and mass distribution were not only stable but also far more mature than expected for an object formed only a few hundred million years after the Big Bang. The dynamical stability suggested a universe with pre-established coherence, one that might defy our current notions of causality. As scientists probed deeper, more peculiarities emerged. The gravitational field surrounding the galaxy was unusually intense compared to its visible mass. While such discrepancies are usually attributed to dark matter, the distribution here didn't match known dark matter halos. It was more concentrated and structured. This suggested the possible existence of a new type of gravitational interaction, an unknown state of matter, or a modified regime of gravity that becomes relevant only at specific scales or energies. Further complicating matters was the galaxy's isolation. In the early universe, galaxies typically formed in dense clusters, shaped by gravitational interactions and cosmic filaments. But this galaxy stood alone, surrounded by a vacuum eerily clean for its epoch. There were no signs of past collisions, no stellar trails, no disrupted arms. This pristine condition raised profound questions. Had this galaxy formed through a radically different process, or had some unseen mechanism shielded it from the universe's chaotic birth? Its structure also defied expectations. The galaxy was not a simple spiral. It bore all the hallmarks of a barred spiral galaxy, complete with a central bar and defined star-forming arms. Such architecture usually requires billions of years of secular evolution and interactions, yet this galaxy had somehow achieved it mere hundreds of millions of years after time began. Was there an accelerated mode of galactic evolution at play, or were we witnessing a kind of cosmic formation that had simply eluded observation until now? The galaxy's colors, too, broke the mold. Instead of the expected red-shifted hues, its light oscillated between ultraviolet and near-infrared wavelengths, fluctuations that couldn't be explained by known Doppler or redshift effects. Some researchers even speculated these might be large-scale quantum interference patterns, possibly magnified by exotic gravitational phenomena. Others proposed that this wasn't a single galaxy at all, but a gravitationally entangled echo of multiple galaxies, either lensed through spacetime or distorted by unknown relativistic effects. In the wake of this event, theorists revisited old satellite data from Hubble and Spitzer, wondering if they had missed similar anomalies. Retrospective analyses revealed faint, ambiguous signals that may have been misinterpreted or overlooked due to noise thresholds and confirmation bias. Perhaps the impossible had been in plain sight all along, dismissed because it didn't fit our models. One of the most profound implications of this discovery involved the nature of time itself. New models began to entertain the idea that time might behave differently across various regions of the universe. The concept of cosmic time bubbles emerged, zones where time dilates or contracts due to fluctuations in the energy density of space. If true, the galaxy may not have evolved quickly, but rather at a normal rate inside a bubble where time moved more slowly. From our perspective, it would look as if the galaxy matured impossibly fast, when in reality it followed its own unique clock. Another radical interpretation invoked the holographic principle, suggesting that the universe is a three-dimensional projection of information encoded on a distant two-dimensional surface. Under this model, the galaxy might not be a real object at all, but a kind of rendered representation, perhaps even a glitch in the cosmic code itself. The idea drew from theories in string physics and black hole thermodynamics and hinted that what JWST had uncovered was not just a celestial body, but the underlying algorithm of the universe itself. Astrophysicists also began examining inflationary anomalies in early universe theory. If certain regions expanded differently after the Big Bang, they might have developed radically unique local conditions. Perhaps this galaxy formed in a slower inflating pocket of space, where time and matter conspired to create galaxies with breathtaking speed and complexity. In this scenario, the universe would resemble a patchwork quilt of different laws and timelines, each evolving independently. Meanwhile, scientists began integrating high-resolution gravitational wave models to further study the anomaly. Analysis through gravitational wave detection at such a vast distance remains within the realm of theoretical ambition. To gain insight, simulations were conducted to estimate the kind of gravitational signatures a galaxy of this nature would produce if it had interacted with its surroundings. The resulting data showed ripple patterns that didn't match those typical of black hole or neutron star mergers. This led to the bold proposition that this object may have formed through an entirely different gravitational collapse mechanism, perhaps from the collapse of an exotic form of matter or even a relic cosmic string from the early universe. As the James Webb Space Telescope, JWST, continued its mission, it became clear that this galaxy was not a temporal outlier but one of many similar anomalies. A second, then a third, and eventually half a dozen galaxies were discovered under comparable cosmic conditions, all defying known rules of time, mass, light, and structure. While not identical, each displayed developmental anomalies, rich in metals, disproportionately massive, or morphologically complex far beyond their expected age. The statistical improbability of so many coincidences made it difficult to attribute the findings to observational errors or instrument glitches. A new cosmological model was urgently needed, one that didn't just tweak existing parameters but fundamentally rewrote the rules of the universe. These discoveries also rejuvenated the field of exoplanet research. If galaxies were evolving more rapidly than expected, could planets have formed earlier too? This raised the tantalizing possibility that ancient civilizations or biospheres might have existed long before Earth had even cooled. Signals previously dismissed as noise or interference were re-examined under this new light. Astrobiology expanded its scope, no longer limited to searching for life that might exist now, but also including the quest for life that may have risen and vanished in the deep past. The role of black holes also became increasingly central to this narrative. A new hypothesis suggested that early black holes may have served not only as galactic anchors but as cosmic accelerators, regions where matter, energy, and even information were transformed in ways we have yet to model. If primordial black holes had properties beyond our current understanding, if they could spawn stars, seed galaxies, or even induce localized expansions of space, they might be the architects of these impossibly early galaxies. This spurred cross-disciplinary collaboration among quantum physicists, data scientists, and philosophers of science, all grappling with a universe that defied linear interpretations of history. To uncover hidden correlations among these anomalies, artificial intelligence tools were employed to sift through terabytes of observational data. Machine learning algorithms began detecting subtle patterns that hinted at a deeper cosmic structure, a kind of fractal rhythm, an underlying symphony of form and energy playing out across scales beyond human comprehension. Theoretical cosmology, once a discipline driven largely by elegant mathematics and philosophical speculation, now had a wealth of raw data to examine. This impossible galaxy became the cornerstone of what some began calling cosmic archaeology, the study not of what is merely far away, but what is deeply buried within the fabric of spacetime itself. The universe, it turned out, had kept secrets not just in its vastness but in the complexity of its unfolding logic. The Webb telescope's impossible encounter didn't just challenge scientific consensus, it shattered the illusion that the cosmos was fully charted. It reminded humanity that the universe is not obligated to be comprehensible, and that even our most advanced tools may still be drawing incomplete maps. Scientists around the world, now peering deeper into space, recognize that the legacy of this discovery isn't confined to datasets or academic papers. It lives in the realization that space is no longer the final frontier, it is the beginning of something far more profound. As the Webb telescope delved further into the early universe, it uncovered a realm that seemed alien not just in distance or scale, but in its very logic. What began with the discovery of a single mature, structured galaxy soon expanded into a pattern of peculiarities that could no longer be dismissed as anomalies. These outliers collectively hinted at a deeper cosmological architecture, leading scientists to target similar epochs. The new observations became even more inexplicable, galaxies with unusual chemical richness and element ratios inconsistent with known nucleosynthesis patterns. Some even displayed high concentrations of elements like magnesium, silicon, and platinum, implying stellar recycling on timescales that had not yet passed. This raised the possibility of an undiscovered mechanism, perhaps an ultra-efficient star formation process, or a non-stellar origin of heavy elements. One radical hypothesis suggested that early particle interactions could synthesize complex elements directly, without stellar fusion. If confirmed, this would overturn the long-held belief that stars alone forge the periodic table, implying that the early universe might have had complex chemistry akin to our solar neighborhood from the very beginning. Further intrigue came from the spatial distribution of these galaxies. Instead of the uniform structure predicted by cosmic inflation and the cosmic microwave background, these galaxies appeared clustered in a loosely coherent pattern, hinting at an invisible cosmic architecture. Some researchers began exploring whether higher-dimensional influences or dynamic local geometries could be shaping matter and energy, prompting renewed interest in the topology of the universe. A bold new idea emerged, that spacetime itself might experience localized phase transitions, subtly altering the curvature and structure of reality and allowing for unexpectedly rapid development of cosmic structures. Compounding this mystery was the discovery of galaxies exhibiting synchronized starburst activity, waves of star formation sweeping across them like coordinated signals. This coherence could not be explained by internal processes alone. The possibility of a quantum field relic from the universe's first microseconds began to gain traction, a background oscillator, regulating processes across galaxies that should otherwise be causally disconnected. Meanwhile, attention turned inward. Could Webb's unprecedented sensitivity be picking up phenomena beyond the electromagnetic spectrum, perhaps even exotic quantum fields? Some speculated that Webb might be detecting remnants from previous cosmic cycles, echoing the controversial theory of conformal cyclic cosmology, which proposes that the universe undergoes infinite epochs of expansion, each leaving subtle imprints on the next. Additional strangeness emerged in deep space regions devoid of visible galaxies. Background fluctuations and low-level energy signatures were detected, too structured to be noise, but too faint to represent known matter. These patterns resembled theoretical profiles of decaying vacuum energy or residual energy states from early inflation, suggesting our universe might still be settling into its physical laws. Webb's polarimetry instruments added yet another twist. In some galaxies, The polarization of light did not match known scattering or magnetic interactions. Instead, it hinted at interactions with chiral particles, particles with orientation-dependent behaviors. This asymmetry raised the possibility that matter's dominance over antimatter might stem from a fundamental bias written into the fabric of the cosmos. Astrobiologists were especially intrigued. If this handedness extended to organic molecules, it could imply that life's basic building blocks, amino acids, sugars, nucleotides, might have originated with a universal symmetry bias. Finally, a more philosophical idea took shape. What if these anomalies weren't distant truths, but artifacts of our observational perspective? If space and time are curved and expanding uniquely at our location, we might be misinterpreting distant observations through a localized lens, mistaking local truths for universal laws. Rooted in anthropic reasoning, this idea suggests that our cosmic understanding might be fundamentally skewed. In closing, if you enjoyed this exploration, please like the video, subscribe to our channel, and share your thoughts in the comments. What do you think about JWST's impossible deep space encounter? We'd love to hear from you. Thanks for watching, and we'll see you next time.